moment of inertia. So this one's a little bit out of step, but we've been doing all these calculus things with masses and densities and things. So I thought I would present it now, and then we're going to start talking about kinetic energy of shapes, and then this thing's going to pop out. And so when we get there, you'll at least have seen it once, and hopefully that makes it a little bit easier. So the idea here is when we computed the center of mass, we computed the average position of, or the average value of x or y. Roughly, what we want to do now is calculate the average value of x squared or y squared. Roughly, it's not exactly that, but it's sort of close to that. So it kind of works out the same. More precisely, what we imagine is that we have an object. So let's just say I've got a cylinder. It doesn't have to be symmetric though. And this object is rotating in some way about an axis. I'm going to put the axis right down the center, but it could be any axis. It could be over there. It could be on Jupiter. If this thing is somehow going around some axis. And what we would actually want to do is determine, so you want to think of this object as kind of like a whole bunch of little cubes. And for each cube, we want to know what is the perpendicular distance to the axis of rotation. Okay, so I would call this, let's call this distance D. No, that won't look good. Let's call this distance R. All right. So each little piece could have a different R. And the definition of moment of inertia is it's just going to be defined to be this. For a 1 point mass, moment of inertia, the symbol for it is I, and it's the mass times R squared. That's for just a point mass. But if you have a 3D shape, it actually equals the integral of, you can write as dm r squared, or you can write it as the integral of r squared times rho dv. Okay, so it's similar to what we had for the center of mass or just the total mass, because it's a density over a volume or density over an area. However, instead of x here, you put the perpendicular distance to the axis of rotation. We aren't going to calculate these quantities. Then instead, if you need these formulas, for different shapes are going to have different values of I, and they're more or less standard formulas for symmetric, nice shapes. So I'm going to switch screens here and give you kind of a web page that has a list of the common ones that you might need for doing homework. But it really, it's calculating kind of the average of the perpendicular distances, where it's the distance perpendicular to the axis of rotation. So what's going to happen is we're going to have these objects spinning around some axis caused by some torque or twist, and I is going to be an important quantity for characterizing how things actually move. So I'm going to change screens now so you can see a list of these moments of inertia, so that when we get to it here in a video or two, you're not too surprised. So here are some common moments of inertia, and the actual formula you get changes whether you are looking at rotations along, like through the body, an axis which goes through the body, or an axis which kind of slices, kind of pokes straight through the sides. So I wouldn't bother to memorize these. To be honest, the ones that are here are about the only ones I ever remember personally. And So the important ones would be a solid cylinder, and you get 1/2 mr squared. R, the perpendicular distance, just is the radius of the cylinder in this case. If it's a hoop, so that'd be like a hollow cylinder, then you get I equals mr squared. So when you have a solid cylinder, it's a half. When it's a hollow one, it's a 1 sitting there. If it's a solid sphere, you get 2/5 mr squared. If it is a hollow sphere, so a thin spherical shell, you get 2/3 mr squared. If it's a rod rotated around its center, you get 1/12. If it's a rod rotated around its end point, then you get 1/3 ml squared. So notice in all cases, the moment of inertia is always some sort of a fraction, some sort of number times m times a length squared. Now, I shouldn't say always. This is for simple shapes. For more realistic shapes, it can be quite complicated. But in practice, even when you have something that's really complicated, you can break it down into a combination of simple shapes. So usually this list will allow you to get pretty close to the true value for any shape, whether it be regular or irregular. Okay, so that kind of is our video series on describing kind of the mass and of extended shapes. We've talked about mass, we've talked about center of mass, we've talked about and now we've talked about moments of inertia a little bit. We'll come back to that a little bit more heavily as we get to rotations. All right.